Uh, I'm sure. Even when I was studying, there were, I faced a lot of doubt in imagining the lattices and what exactly is a unit cell. How does this exact thing work? Imagining the part. So, that was one problem. The other problem was with close packing. How do we relate close packing with lattices, or do we even relate close packing with lattices? So, because of this particular thing, we have this doubt. So, we already know that CCP is equal to FCC, but we are unable to visualize that. How can ABC layer be same as face centered cubic? They sound so very different. We studied them in two different sections. They look so very different. So how are they same? Right? That was one of the doubts. A major doubt, and out of the 50 plus comment that I received, I believe 50% of them were on voids itself. That is one thing that I really want to concentrate on. The voids. Right? Yeah. After that, we'll take a few questions which are very typical, and questions on which we face a lot of issues while solving them. So we'll deal with that as well. Now, let's start. Let's start with the lattices. Uh, Now, one more thing before we start. The live chat is now available. So if you have any doubts in the session as well, you can post it. But be considerate over there. I'm sure all of you know that what you're receiving at your end is a slightly delayed thing. So I will take your doubts, but at a certain interval later on, right? Okay. Yeah, so let's start with lattices. What exactly is lattices? We hear this word for the first time in 12th standard, right? I mean, I don't know about all those who have been preparing very consistently since 8th or 9th, but I heard this for the first time when I went to school and studied solid state, right? So what exactly is lattices? Okay, so when you see a building or a wall being constructed, the smallest unit, and this is a very typical example that I'm taking, the very smallest unit of that wall is a brick, and a lot of these bricks, together construct that building. The wall. So you have one wall, and then the second wall, third wall, a roof, and so on, and that is the whole building. But if I were to break it down to the smallest possible unit, which on repeating would give you the entire structure, right? This smallest unit is basically a unit cell. So that is the distinction that we have, right? That is the distinction that basically we have between unit cells and lattices. So lattice is the entire structure. The entire diamond structure would be a lattice. The smallest possible block within that would be your unit cell, right? The entire structure of NaCl is a lattice, right? And it will have some lattice energy as well. And the smallest possible unit of that, which is basically an FCC lattice of Cl minus, or maybe Na plus with the other ion in voids. So that is a unit cell, right? So that is how it basically works, right? I have a few figures here just to clarify one small doubt. The lattices that we study, the lattices that we come across in our books, they are very geometrical, they are very regular. That is not the entire case. The lattices can be of any different types, right? We only study the geometric shapes, and even within that, as far as the unit cells are concerned, we only study the 3 unit cells, the FCC, the BCC, and the simple cubic. We don't even study HCP, completely. We have a slight introduction of HCP, but that is it, right? So anyway, just to summarize, lattice is the huge structure that you're looking at. Unit cell would be the smallest possible unit of it, the brick that makes the entire wall, right? Now I was showing you this figure because, like I said, in NCERT you have all those regular shapes, squares maybe, or hexagons maybe, right? What would be the unit cell in this particular shape, or maybe in this shape, or maybe in this shape? It's kind of difficult to see, right? So it's not exactly very regular all the time, and if you're facing issues, it's okay, right? But remember that in your syllabus only regular shapes are there. These irregular or unsymmetric shapes are actually not there in your syllabus. You'll probably study this in the second year of your engineering in the course called material sciences. But for now, for JEE, you only need regular shapes, cubic or hexagonal or monoclinic, rhomboclinic, etc., etc. Right? For the rest of them, only the dimensions are important because they're listed in a table. You might want to learn them, but for detailed discussion, we only go for BCC, FCC, and simple cubic. That is it, right? that is what we have on lattices. Okay, more people are joining in here. Let's see. Raj Singh, hello. Nanak Singh, yeah, a very good evening to you too. So Raj Singh wants to know about crystalline structure and packing efficiency. Okay, we'll come to packing efficiency in a short while. Let me take up crystalline structure. So, before we come to unit cells and lattice structures, we have a small section in which we categorize solids, right? So, as far as solids are concerned, we have two forms, right? We have the amorphous and the crystalline. So crystalline is generally defined as the form of solid in which you have a single pattern being followed throughout the structure, right? So I'm sure while you were traveling in trains, you've always come across all those forests, on your left hand side or your right hand side, on the window side, where the trees are planted in a very regular fashion. They're in a single sequence, a single line all the time, right? There's a fixed distance between each of them and there is no abnormality at all. So that kind of an arrangement within a structure, so every atom or every position is basically at equal distances or at equivalent distances from each other, right? A set pattern is being repeated throughout, so that is what we call as crystalline, right? The amorphous is the opposite one. So if there is ever a break in symmetry, if there is ever a break in that entire pattern, it is going to become amorphous. So I could use that exact diagram that you have in the NCERT. So in amorphous, you have, let's say, hexagons or triangles or squares, all of them together. So there is no set pattern. But within crystalline, you'll have a set pattern, a fixed pattern being repeated all the time, all throughout, from one end to the other end, from the bottom to the top, everywhere. Keep in mind that over here we are talking about the exact definitions, as in what would be the exact crystalline, a perfect crystalline and a perfect amorphous. The actual solids that we have, they have a lot of defects, as we will study later on, right? Okay. Yeah. So moving on to what we were discussing within lattices. Let me just erase this part. Yeah. So within lattices, we have about 7 different types of lattices, as you've studied, and for each of those lattices, you could have 4 different varieties. What are those 4 varieties? Simple, body-centered, end-centered, and face-centered. Right? What is simple? Simple is a case in which your points are only at the corners of your unit cell. That is it. Corners and nowhere else. Body-centered, as the name suggests. So you have points on the corners. Let's take a very simple example here, right? So this is simple, very straightforward. Body centered, when you have something at the center of the entire body. So I have a cube, I have atoms or basically ions at the regular positions, the corners of the cube. So 8 atoms over there. I additionally have one more at the center of the cube, at the body diagonal, at the intersection of the body diagonal, right? So that is body centered. End centered means I don't have a body center. I only have, in addition to these, I also have, lattice positions at the face centers, the opposite face centers, right? So if I have at the top, I will have one at the bottom, and that is it. So that becomes end centered, right? If I have on the left side, I'll have one on the right side, and that is I won't have anywhere else. So that is end centered, right? Kind of a subset of face centered. In face centered, you will have lattice position at the center of all the faces. You will have no lattice position on the body center, right? So in addition to these corners, additionally you will have the face centers having lattice positions. So that is face centered. So these are 4 varieties, which means for all these 7 lattices, you could have 4 varieties. In total, you should have 28 different configurations, right? But you don't. You only have 14, right? And well, the reason for that is not exactly mentioned in your books, but let me still tell you that the reason for that is very simple. There are few intersecting, lattices, as in the end-centered monoclinic would look very similar to maybe a body-centered some other structure. That is why those two are clubbed together, and that is how we do away with half of these structures, right? And that is why you end up with only 14, not 28. Right? You'll study more about that, as I said, later. Why am I telling you this? This part, it's already there. Most of you already know it perhaps. The reason I'm telling you this is because over here you have a lot of questions on the geometry itself. So one thing that you'll get is on identification of the unit cell, right? So within, let's say, simple cubic, I have about 1 atom per unit cell. You already know that. So how many unit cells are there in a particular crystal, something like that. So that is one variety of question that you get. The other variety of question is on the dimension itself, right? So that is why it's very important to know what is the exact configuration that you have, right? Now, the other thing that I want to highlight here is we generally draw simple cubic like this, like I have drawn here. But does simple cubic look like this? No, it doesn't. See over here, just to highlight, right, that this is making a square, we have made these circles smaller. But remember that actually it looks, this is a incorrect figure. So actually this looks something like this. These are all connected to each other. These are all in contact with each other. That is simple cubic, right? And that is why within simple cubic, if I want to find out, let's say, the dimension of the unit cell, that is going to be 2r, very straightforward. Similarly, now simple cubic was easy, right? Similarly, the issues that you face, I had a question in the article regarding the dimensions of, BCC. So within the, within BCC, how would you find, the dimensions? So within BCC, the structure looks something like this. The corner atoms are not exactly in contact. The inside atom, they are all in contact with the body center atom, right? So if I were to look at the diagonal, it actually looks something like this, the body diagonal. So that is what you have to identify. I know that in a BCC structure, the spheres which are in contact are along the body diagonal. If I know the dimension of the body diagonal, I can find out, I can relate the, the radii and the. So over here, I know that, the body diagonal, if you don't know, you can figure it out. This is going to be √2, right? And within the body diagonal, this dimension is going to be √3, right? So √3a, if a was the size of the, unit cell, √3a is the size of the diagonal, and this is equal to the radii of these many spheres, so 4r. And that is how you figure it out. So even if you do not remember this, most of the students that I've seen, they end up memorizing these relationships, right? And that is why they get confused between what was the relationship for BCC and what was the relationship for FCC. You don't need to do that. You need to figure it out. You need to know how how did this relation come about. That is when you will be able to remember it. You'll be able to retain it for longer. You'll be able to recall it during the examinations, right? So the important part in lattices is actually the dimensions, is the imagination of all of those things. So I will recommend a few videos at the end of this session in an article. You can watch those videos for a better idea of what these lattices look like, right? That is point number 1. Okay. All right. So we'll come to packing fraction in a short while, and my colleague here, Naveen Pratap, is answering a few of your questions. If you have any more questions, you can post it on the chat. If you're posting questions on the article, I can't exactly see that right now. Right. So like I said, go to the YouTube channel of GradeUp and watch it over there so that you can post your queries. Right. Now, this is a question that I was talking about. This question was posted by Sneha Tiwari. Right. And the question was, how many unit cells are present in a cube-shaped ideal crystal of NaCl whose mass is given to you? Right. So over here we want to find out the unit cell. Now when I see this question, the one thing that comes to my mind is I cannot exactly relate the number of unit cells with mass, but I can relate the number of unit cells with atoms. Can I find out the number of atoms from mass? Of course. That is what your entire first standard first chapter of 11th standard was all about, stoichiometry, right? So if you can find out the number of atoms which are present in 1 gram of unit cell, and if you know that effectively NaCl basically has an FCC structure, so that is the second piece of information that you should be aware of, right? And an FCC lattice, within an FCC structure, each unit cell consists of 4 atoms effectively, right? So one unit cell will have 4 atoms. Find out the number of atoms here and divide by 4. That is going to be your answer, as simple as that, right? So let's see. So Cl is 35.5, Na is 23 approximately. So this comes out to be how much? 58.5, right? So 58.5 gram per mole, as in 58.5 grams is the mass of 1 mole, that is 6.022 into 10 to the power 23 atoms. So 1 gram would contain a certain number of moles and therefore a certain number of atoms. Divide that by 4 and that is how you arrive at that answer, right? So this is there within the comments of that article. Everyone please solve it your end and go through that. I will post the solution in the comment of that article as well, as a reply to this particular statement. Like I said, it's a very, very simple question, right? The only thing over here is you need one piece of information here and you need the other piece of information, how to relate the unit cell with mass. So there is no direct relationship, there's an indirect relationship. Unit cell to number of atoms to mass, right? So that is what we have. Now, moving on to the second most important problem that we have, that is close packing. So over here, I'm going to give you a slight structure of the chapter itself. Close packing is not something different. Basically, we are approaching that unit cell from two different directions, right? So first of all, we study about amorphous and crystalline and their properties, and that is one part. And after that, we say, okay, if I want to make this lattice, let me take the smallest possible part and let me repeat that. That is the unit cell, right? So that is one way of generating the entire lattice. This is the other way of generating the entire lattice, and don't be surprised if you arrive at that same result from the other way as well, right? These two are two different paths of reaching the same, right? Same destination, right? For example, I mean, before I explain close packing, if I were to arrange atoms in this fashion, imagine all of these are in contact and they are on top of each other. This would basically be same as the simple cubic unit cell. Right, we call this close packing in 1 dimension or 2 dimension, right? But this is effectively same as your simple cubic. Similarly, you have another version which is CCP, which is similar to FCC. We'll come to that as well, right? So imagine this as another pathway, another way of approaching that same thing. So one thing was figure out the smallest possible unit and extend it in every possible direction to generate the whole lattice. The other was to break up into layers. Right, so within 1 dimension, we take this as our single close packing. You cannot close it any more than that, right? These are spheres. We assume atoms or ions to be spheres. By the way, this is an assumption that you need to be aware of. We are assuming them to be hard spheres, right? So as you study it deeper, we factor in a few more things to account for this assumption. Right. Anyway, so this is 1 dimension. 2 dimension would be either this or let me actually not draw there. Okay, so either this or this. Which one is better? So in this case, I'm leaving this much amount of space. Let me color that with a different ink. Yeah, so this is the amount of space that you are leaving in between, and these are actually voids, by the way. And over here, this is the amount of space that you're leaving in between. So what have we done in these two things? These two are both close packed forms, but this one is a little more efficient than the other. It is leaving out lesser space. To give you a better idea, I have a figure for you. Yeah, okay. This, right, I'll use it again for the voids, right? But over here, let's check this out. Whenever you are packing, which is something which is spherical or oval or something which is not exactly square or rectangle, it will always leave some amount of space in between, right? Some amount of space in between, as you can see over here, right? These are the spaces which are left. There is nothing that you can do to avoid this. Right, and that is why when you pack something spherical or oval, the efficiency, right? I mean, the entire space is not occupied, and hence we calculate what is called the packing efficiency. How much of the space is occupied, right? So let's come back here. Okay, right. Anyway, so this was for 2 dimension, right? So in 2 dimension, I could have one layer like this, and then the third layer comes in here, and then the fourth layer is like this, and so on and so forth. So this is 2 dimension. All you're doing is stacking a bunch of atoms, in a certain sequence. Remember, we are not making the smallest possible unit here and repeating it. We are approaching the same thing. We are making that same lattice in a slightly different way. There was student A who said that, let me figure out which is the smallest possible thing. I will just buy 1000 of those and I'll stack it. Or the other student said that no, let me make layers and I'll stack the layers on top of each other. These two are two different approaches for the same problem, for the same destination, right? So if you keep that in mind, close packing becomes comparatively easier, right? Now, one of the other things that that you have to figure out in close packing is coordination number. That is the question which is generally asked. And again, for coordination number, you have to visualize, right? So over here, coordination number very simply is defined as the number of nearest neighbors which are in direct contact, right? You have this number coming up again in a later chapter, in coordination compounds. So over there also it means the same thing. Over there, ligands are approaching a central atom, and the number of ligands that come in and bind with that becomes the coordination number. So it's the same thing. Coordination number is defined as the number of nearest neighbors. That is it. The number of neighbors which are in direct contact, right? So over here, as you can see, it's 4, and right. Yeah. So over here, as you can see, it's 4. Over here, as you can see, it's 6. And obviously, this is better packed than this one. It is leaving lesser amount of space than this one. So obviously, this one will have a better packing efficiency, right? If you were to find out the total volume of a certain rectangle and the volume occupied by these circles, you will get a higher ratio as compared to this one, right? That is it. That is packing efficiency. Okay. Let's go ahead. Now, in close packing, like I said, when it comes to 3 dimensions, that one layer you're just repeating it on top of the other. Now, over here, this is what you've studied. Right? Let me write that down. So over here, this is what you have actually gone through. So you have basically talked about 2 types of packing. One is AB, 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 and so on. And this is what ultimately generates HCP, hexagonal close packing. We'll see how. Right, and the other that you've studied is ABC, 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 and so on, right? And the other is CCP, right? And one of the questions that I had was, okay, HCP is the hexagonal one, the CCP is FCC one. What is BCC in close packing? BCC is not a close packing, right? In BCC, you have one atom surrounded by 4 of its neighbors. There's too much space which is left. Right. So we in our book, in our syllabus, we have only concentrated, as far as close packing is concerned, we have only concentrated on the ones which have a highest efficiency. That is HCP and CCP. They have the highest efficiency. Right. We haven't really covered all the rest of the cases. But I'm sure you can imagine, right? ABC is one. I'm sure if I were to say ABC, then again ABC, this would be another form of close packing, kind of a mixture. Right. If I were to go for, let's say, ABC, BC, BC, again ABC, AB, this is another form of close packing. My point is, if we are just stacking layers on top of each other, there are not just 2 varieties. There are more than 2 varieties. Right. There are so many different varieties. We have only covered these 2. So don't be confused if you somehow feel that there are gaps in between. Like if it's if CCP is FCC, what is this? Right. That's not required. We're only studying a certain part of the chapter to get a certain idea. But I like the fact that the person who asked that question was very curious. That's a very decent question. Okay, so close packing is basically stacking in such a way that you save a lot of space, right? That your efficiency is comparatively higher. That is close packing, right? Now, let's see. I want to know whether. Okay, so Dev Chaurasia, I'll take it out in a very short while. And Harsha KJ, hello, welcome. Umesh, yes, hi, welcome to the session. All right, yeah, so no other doubts. Let me take Dev Chaurasia's doubt in a short while. All right, let me talk a little bit about packing efficiency first. Right, just ignore this glitch in handwriting. I don't know, maybe I have some issues with the stylus or something. Anyway, so packing efficiency, what exactly is packing efficiency? So packing efficiency is, I had a big box, right, and I wanted to pack mangoes in it. How many mangoes can I pack over here, right? Can I occupy the whole box with mangoes? Obviously not. Mangoes have an oval shape, right? So they will not occupy the entire volume that is available, right? So let's say the volume that I have available over here is V. That is the volume of the box. Let me call it VB. and each of the mangoes have a volume of, let's say, Vm, right? And over here I'm stacking mangoes. So let's say these are the number of mangoes that can be stacked. How many? 9, right? I know that 9 Vm is going to be less than Vp. Packing efficiency just tells me how much lesser. What is the percentage, right? So 9 Vm divided by Vp into 100% is your packing efficiency. Apply that to FCC. So within FCC, let's say the volume of the box is going to be A cube. That is the volume of the unit cell. The volume of the mango is going to be the volume of the atom itself. We are assuming it to be spheres. So 4 by 3 pi r cube. And within FCC, you have 4 such things, right? So 4 into 4 by 3 pi r cube upon A cube. This is the packing efficiency. That is it. If I want to simplify further, right, I will find out the relationship between A and R, which I will already know since I've studied the geometry. Within FCC, I know that the face diagonal is where things are in contact. So within the face diagonal, 1, 2, 3, root 2 A. Let me write it here. Root 2A is going to be 4R. Just apply this relationship and you have the packing efficiency, right? So very simply speaking, packing efficiency is just the volume occupied divided by the volume that was supposed to be occupied, the volume that was available, right? So volume occupied upon volume available into 100%. How much of the available volume were you able to pack, or was that atom element able to pack? That is packing efficiency. That is it. As simple, right? And the relationships that you've studied for BCC or simple cubic or maybe FCC, they come in handy when you're simplifying these terms. That is it. Otherwise, this is a good enough answer. You won't probably get marks in boards for this answer. You'll probably get, maybe it's a 3-mark question, you'll probably get 1 or 1.5. You won't get full marks. But effectively, this is packing efficiency. That's it. Right? Now, let me show you. Let me clear this. Okay, so let me show you how the voids come about, and simultaneously let me talk about AB structure, right? So imagine this is one particular structure. We're looking from the top right here, right? So we're looking at the top of this. This is one particular close packing, one layer, right? Obviously, I'm going to call this A. As always, every book does that. Every video does that, right? So this is A. Let me bring in the second layer, right? So again, I'm trying to save some space, right? So what will I do? I'll try to occupy all the little holes that were there. But what do I notice here? I notice something very interesting. Yeah, what I notice here is I cannot occupy all the holes. Let me go back, right? So these were all the holes that were available to me. Do you see that? These were all the holes which were available. But if I bring in the second layer, I'm only occupying one set of the holes. The other set of the holes will remain unoccupied. If I maybe shift this layer to occupy the other hole, the first one will remain empty, right? So you cannot occupy all the holes by the second layer. Absolutely, you will only occupy one set of the holes. Now, so this is where I'm going to tell you that all the holes which have been occupied, this one, these 4 atoms together, they make the tetrahedral, and these 6, they make the octahedral. So we'll talk about that in a short while. But this is effectively my layer B. Now after that, as you might have studied, I have a choice. I can bring in the second, the third layer. Either I can put the third layer right on top of the first layer, like this. So I won't exactly call it C or D, right? This is same as A. So this is what we call AB structure, right? This is AB structure. We'll see what it makes later on, but this is our AB structure. This is a 3D close packing. Right? Let me, slide this layer a little bit. Let me remove this. Let me bring in the third layer, which occupies all of these holes. These ones. There. Right? This is a different layer. This is not on top of any of the pre-existing layers. Right? So this third layer, let me call that C. That is one structure. Now, when I bring in the fourth layer, it is going to be on top of A. If I have a regular ABC type. That is why we have. If I want to make a very ideal situation, we have 2 options, either AB type or ABC type. These are 2 ideal situations. And in these 2 ideal situations, right? So I hope everyone is clear with the stacking part. All I've done is, the blue layer, all I've done is I've shifted the green one slightly to occupy these holes. That is it. I've shifted it slightly. That is why there is no difference in packing efficiency of these two packings. This is there is, however, difference in how they look, what is the unit cell that they end up making, and all of those things. There is difference in that, but there is no difference in packing efficiency. That is why, one of you maybe asked a question as to why HCP and CCP are different, right? So this is where they're different. They have the same packing efficiency because all you've done is shifted a layer, but by shifting that layer, you have effectively changed their shape. One is ABC type, which is going to make cubic. The other is AB type, which is going to make hexagonal. Two different shapes, right? With two different unit cells, of course. Okay. Let's see. More doubts are coming in. That's great. So how to find coordination number? I'll take that in a short while. Yeah. So this is the this is what you get. AB type, that is hexagonal. Why do we call it hexagonal, by the way? We'll see that. And this is cubic. Why do we call it cubic? Right. The reason is the AB stacking. When you find out the unit cell of that is actually simple hexagonal. So hexagonal is one of the Bravais lattices, and within that, the simple one is basically what is generated by this one. And this is called cubic because the unit cell that it generates, the Bravais lattice that it generates, is same as FCC. That is why you call it cubic. These names, the cubic and the hexagonal, they are not by accident, right? So the unit cell which was generated by this closed packing was basically hexagonal, or the unit cell which was generated by this one was basically cubic. That is why they have these names, right? And this is where I come into that very important doubt: how is CCP same as FCC? Now over here I don't see a cube. Do you see a cube? I don't see a cube at all, right? So this was one of the doubts which was really very difficult for me to solve when I was studying. How is CCP same as FCC, right? Anyway, so this is how they are same. In this case, right now what you're seeing is one form of its representation, where we have stacked the layers on top of each other, right? Within FCC, imagine that same stacking in a diagonal space, right? So this is one layer, the red one. This is the other layer, the gray one. The blue one is the third layer. So A, B, C, and then again the red one. This is again A. Now, is this looking like a cube? I don't know. Probably not. Let me see if I can make it look like a cube. This is one of the faces. Yeah, so these four cubes together make one of the faces. We shade it. Right, so this is one of the faces right here. This is the front face that you see over here. Right? Okay. Now, this ball right here is the center of the face. These four are the corners, right? So that is how this is the first face. So one layer is not forming one face. Within a single face, you have atoms from three different layers. The first layer, the second layer, as well as the third layer, right? And actually the stacking is in the form of a diagonal. This is one, let's say this is one corner. This is the exact opposite corner, right? So the stacking is in the form of a diagonal. It's not exactly vertical or horizontal. It's in the form of a body diagonal, right? So that is how the atoms are arranged. So if you were to imagine a room, right? One corner of the room, that is layer one, right? The corner, the face centers, they form the layer two. Then you have layer three, and then you have layer four at the exact opposite corner, right? So that is how the stacking goes, right? So yes, ABC stacking is actually FCC. You have to tilt it slightly, right? So instead of viewing it horizontally or vertically, right, you have to view it as a body diagonal. That is how you will be able to realize it. Again, I will basically share a link for a video where this is very nicely explained, right? Okay, all right, now moving on to the hexagonal part. In the hexagonal part, we don't have any such issue in the imagination, right? So all you have to do is take the A layer, this is the B layer, take the C layer, right? That's it. And if you look at it from any particular direction, this definitely makes a hexagon. So over here, there is no such confusion, right? So this is hexagonal close packing, right? Okay. Now, so I hope all of you are clear as to how CCP and HCP are different. They are different because this third layer that you place You decided to place it right on top of the first one instead of occupying the second hole. It did not change the efficiency, it just changed the overall form that the the structure was taking, right? Okay. Now let's see. Bihan Chatterjee, this is a live session on class 12th where we are talking about solid state, right? And yeah, I believe that is all the doubts. Moving on. Now let's talk about voids, right? So this was again one of the most pressing issues that I saw. Like I said earlier, out of the 50 plus doubts that I received, 50% were about voids. What exactly is voids? And as I said earlier, as is highlighted over here itself, right? These spaces which are left in between, which are not occupied. Remember we talked about packing efficiency. So there is a certain amount of space which is not getting occupied. That space is basically the void. The literal meaning of void is empty space, space which is not occupied by anything. That is a void, right? Now we have two types of voids because of the stacking that we have seen. One type of void is this, the one that is formed when you placed the second layer on top of the first layer. So the space which was slightly occupied, that is one type of void, right? So this is, since it is being formed by four different, atoms, when you join their centers and you form the solid, that solid looks like a tetrahedron, right? So that is why this is called a tetrahedral void. Simple, right? The other type of void is basically formed in this case, this one, right? The void which is not occupied by the second layer as well. So over here, when you join these centers, these three spheres and the bottom three spheres, when you join them together, right, you get an octahedron, and hence this is called an octahedral void, right? So that is how the names come about. So one is the void which is basically being formed by four spheres in direct contact with each other, three in one layer and one on top of them, right? So that is a tetrahedral void. Octahedral void is the one which is being formed by three spheres in one layer, three spheres on top of them, but still you can see the void. That is the octahedral void, right? Let me show you images as well. So this is what a tetrahedral void looks like. As you can see, this is a tetrahedral structure right here, right? And this is what an octahedral void looks like. So when you were to join all these shapes and structures, you will get an octahedral void. So that is what we have. Okay. How to find out nearest neighbors? Yeah. So Surya Teja, as we discussed earlier, the way to find nearest neighbors is basically okay. Let's take an example. Let's say you want to find out the number of nearest neighbors in a BCC structure. So just find out how many atoms are in contact with a particular atom. The best way is to take the central atom itself, the body center, that is in contact with 8 atoms of the corner. So it's its nearest neighbors or its coordination number is going to be 8, right? Similarly, right, now you would argue that you've taken the atom in the body center. What about the one in the corner? Will it have a different coordination number? Let's see. So the one which is on the corner, it will be, it will basically be touching, right, the body central atoms of 8 different cubes, right? Remember, one atom is being shared by 8 different cubes. Similarly, it will be touching the body centers of 8 different cubes. So that will also have a coordination number of 8. In fact, you'll notice this, that whether you pick a face center or the edge center, I mean the face center or maybe the corner, the packing efficiency, the coordination number remains the same. So for FCC, the coordination number is going to be 12, right? For BCC, the coordination number is 8, and for simple cubic, the coordination number is just 4, right? Okay. Yeah. So this is what we have. The voids. This makes a tetrahedron. This makes an octahedron, right? I'll share details about the geometries of these in the notes that I will be sharing after the live session. So within the notes, you'll see how to find out the radius ratios using which you can find out the dimensions of the octahedral void. Again, that is not exactly what is given in the NCERT, but if you're interested, you can go through that, right? Questions on that are also not asked in JEE Main, but maybe you would have questions on that in advanced, where advanced really wants you to figure out the dimension. So it's better to just learn it beforehand and be surprised in the examination, right? Okay. Now I'm going to take a question, right? That was basically the other thing that was really troubling students. How to find out the formula from the voids or maybe the closed packing or maybe the unit cell itself. How do we find out the formula of the compounds, right? That was one thing which was basically and this doubt was shared by this student Wizard G. I don't know what the real name is, but that is the username on our app. Okay, so over here I have a crystalline solid. This is a very difficult question, by the way. So I have a crystalline solid in which the anions are arranged in a cubic closed packing. The cations occupy 50% of the tetrahedral voids, and there is another cation B which occupies 50% of the octahedral voids, and you have to find out the formula of the solid. So over here, a certain amount of information is required from your part. You need to be aware of these informations, right? Let me write that down for you. Okay. First of all, you need to know how many atoms are there in FCC, right? Of course, I know this is 4. Secondly, you need to know how many voids are there in a particular arrangement. So for that, the formula is very simple. Whatever is the number of atoms that you have in a unit cell, the tetrahedral voids are going to be double of that. The octahedral voids are going to be equal to that. So if FCC has 4 atoms per unit cell, the tetrahedral voids within this are going to be 8, and the octahedral voids within this are going to be 4 itself. Remember, this is 2n and this is n itself. If n is the number of atoms per unit cell in that particular unit cell, right? So this is the information that you need to know beforehand. I believe we were able to work this out on our own. This is effectively the only information that was required, right? That is 4. Now, the way to find out the formula of a solid is just figure out how many, what is the ratio between all the constituent, ions that you have within one unit cell, right? Effectively, how many cations or anions, or what is the ratio between cations or anions in that one unit cell? That is what you have to figure out here. So let's see. I have 4 C's. I believe all of us will agree on this, right? Because they are arranged in a cubic closed packing. We just saw cubic closed packing is basically face-centered cubic unit cell, right? So we have 4 C's which are there. They are occupying all your corners, and they're occupying the face centers, right? That is one. Secondly, I have one cation A which is occupying 50% of the tetrahedral voids. How many tetrahedral voids do I have? I have 8 tetrahedral voids. 50% of that is going to be 4. So I have 4A as well. I have another cation as well, which is B, and that is going to occupy 50% of the octahedral voids. The spelling is slightly incorrect, but anyway, 50% of the octahedral voids. I have 4 octahedral voids, half of that is going to be 2. So I have 2 B's. Just arrange them in the simplest possible ratio. So A is to B is to C is very simply 4 is to 2 is to 4, or a simple ratio would be 2 is to 1 is to 2, and therefore this is the answer right here. A2, B and C2. Very simple. And this is exactly what you have to do in any, this was a very simple question, of course, but this is exactly what you have to do in any complicated question as well. So within a complicated question, maybe things will not be as simple, right? Maybe, it'll have a certain different percentage of tetrahedral or octahedral voids, or maybe it'll be difficult to figure out the octahedral or tetrahedral voids, or maybe it is occupying only certain octahedral voids, the octahedral voids on edges, or maybe the octahedral voids in the center. There will be some complication, but this is exactly what you have to do in every situation, right? So this was basically my preparation agenda when I was preparing. Find out the simplest way to solve a particular question and see that if that way is applicable to every scenario, right? So that way you will be able to solve every possible question on that topic. After that, the second step is to find out if in different those unusual scenarios, if there is any other way to do it. That is the second step. The first step is to actually solve the question by your own way, and then figure out if there is an easier way to do this, right? That basically helps you out. Why? Because point number 1, since you have already solved the question by one particular way, you grow confidence on that particular technique, that if nothing else works, I will be able to solve it using this at the very least. It'll take up more time, but yes, I will be able to do it, right? By the way, JEE Advanced, there is never a lack of time. JEE Mains, you may have some lack of time, but JEE Advanced, no lack of time. You have a lot of time. The questions are very less, right? Anyway, the second thing does is, in all those unusual questions, when you are trying to figure out, right, how to, what would be a different or a faster way to solve this, you're basically digging deeper into the topic. That gives you new insights, new understanding. And the more time you invest in this, so maybe some of you at this point of time are really frustrated about the fact that I'm taking 2 hours to solve a question or 3 hours to solve a question. That is not time waste. That is time being invested in something. So if you really tried from your own point of view to solve a particular question for 3 hours, you went through a lot of books, you went through a lot of Google links, you talk to a lot of people. That is, in all of those conversations or discoveries, you're basically adding something to your knowledge. So investing time in solving those unusual questions is important, very important. If you want to go to the level of JEE Advanced, that is the only difference between JEE Mains and Advanced. JEE Mains are direct formula based, you practice a lot, you will get through. JEE Advanced is a deeper insight. How do you get that insight? By solving and introspecting, actually analyzing every question, right? That is a slight, detour that we took. Moving on to the third question, right? Magnetite is basically a magnetic oxide of iron that is used for preparing, tapes. It crystallizes with iron occupying 1/8. Like I said, it's not 50%, it's something else. 1/8 of the tetrahedral voids and half of the octahedral voids in a closed packed array of oxide ions. What is the formula of magnetite? Right? Okay. Now let's see. Let me clear this. Yeah. Let's see if we can solve this. So I have a closed packed array of oxide ions. How many oxide ions will I have? O2 minus is going to be 4, right? In the other case, of course, the tetrahedral voids are going to be 8, the octahedral voids are going to be 4, right? So I am occupying 1/8 of the tetrahedral void. So Fe is occupying 1 tetrahedral void and half of the octahedral voids, as in 2 octahedral voids. So Fe is 1 plus 2, oxygen is 4. I believe we have arrived at our answer. Fe3O4. That is it. That is it, right? So this is one variety of questions. Let me see if there are more doubts. Density. Okay, yes, that is what I will have a question on density. Okay, maybe it's a next question. We'll come to density in a short while. Ashutosh, what else? Okay, nearest neighbor. So we've already answered that. All right, moving on to quizzes. The questions that we have basically solved in quizzes. I basically took a bunch of those questions to cover the topics. Let's see. So over here, I have a solid crystal A, right? And the atom are in CCP array. The B atoms, they occupy the center of the body and the edge center position. So basically, they are occupying all the octahedral voids, right? Obviously, the formula of the compound is going to be AB. Now, if 4 A atoms are removed from the corners, what is the formula of the compound? Right? So that is the question here. If I remove 4 A atoms from the corner, what is the new formula of the compound? Okay. Now, tell me something. If initially, basically initially I had 8 B atoms in the corners, right? And I'm removing 4 of them, right? So I'm left with 4, right? Each of these 4 atoms that you've removed, right? What was their contribution? One thing is, I know that, the B atoms, there are 4 B atoms within the unit cell. I've removed 4 atoms. Should I subtract it and go to 0? No. The one thing that you have to keep in mind is the 4 atoms that you removed from the corners, their contribution to that particular unit cell is not 100%. It's actually 1/8, right? So when you remove those 4 atoms, you've actually only removed 1/2 of that. So, that's just, so out of 4, I've removed half, right? So how much am I left with? 4 minus 1/2. That is the amount of B that I have, right? Let's see, how many A do I have now? Number of A's. So, sorry, this is A. The number of A's I have is going to remain the same. I have not removed any D's here. So this remains the same, right? This is still equal to 4. Just take the ratio again, right? So this is 7/2 and this is 4. So my ratio is 7/2 is to 4 or 7 is to 8. Therefore, the formula becomes A7B8. Right? So that is, so only additional point that you have to remember over here is that the atoms which are being removed from this, the 4A atoms which are being removed from this, that they are coming from the corner and the contribution of the corner is not 100%. right? That is the only thing that you have to remember, right? Okay, moving on. Yeah, this is a question on dimensions. So I have a crystal of lead sulfide which has NaCl structure. This is one more thing that you have to be aware of. They may not directly give you the structure of that. They may tell you that it has the same structure as something else. So NaCl is one of those atoms, one of those compounds whose structure is something that we need to remember. So NaCl has a structure called the rock salt structure, and that structure is basically one of the ions occupying FCC and the other ion occupying all the octahedral voids. That is rock salt structure. You could have Na plus occupying FCC and Cl minus at the voids, or in most cases we have it the other way around because Cl minus is bigger. So Cl minus having all the occupying the FCC points, and Na plus occupying all the octahedral voids. So that that is the other scenario that you could have. In either case, I know that this is having the exact same structure. The Pp2 plus or S2 minus has the exact same structure, right? Okay. What is the unit? What is the volume of the unit cell in general? So over here, all I have to do is, if the distance between Pp2 plus and S2 minus is given to me, all I have to do is imagine this. So within an FCC structure, if this is atom in the corner, this is the atom at the edge center, and then I will have another atom in the corner. This is what is given to you. This is the shortest distance, 297 picometers, which means A here. A is going to be 2 into 297. That is A. And therefore, what is the volume of the unit cell? A cube. That is it. You're done. Right? In fact, I haven't really given the options to this question. In the options, the value was same, only the order was different. Right? So you did not even need to multiply this. How much is 2 into 297? You did not even need to do that. All you had to figure out was what is going to be the order, right? So this is picometer, 10 to the power minus 12, cube of that, right? That is how you figure it out, right? Where is cation and anion in Zn and S? Okay, so Zn is the cation, S is the anion, and they basically have a body-centered, arrangement. So you could look at it in both ways, Rohit Vyas. Either you can have Zn in the body center and S occupying all the corners, or you would have Zn occupying all the corners and S in the body center. Either way, the story remains the same, right? So you could start with Zn occupying the lattice positions and S is in the middle, or the other way around. You will still get the same formula, you will still get the same structure. So it doesn't matter. There is no fixed answer for this. If you write Zn for body center and S for corner, it is still right, or the other way around is also right, right? Okay. Moving on, I have the next question. So yeah, this is where I answer the question on density. How to find out density? First of all, let me I'm sure all of you know what is density, right? Density is, in a very general case, it's a physical quantity which is mass by volume. In solid state, density is not something new or unusual. It is still mass by volume. To find out the total mass which is occupied within the unit cell, you divide it by the volume of the unit cell. That is it. In fact, we can derive, if you don't remember the formula, you can derive the formula right here, right? So density is, like I said, mass upon volume. Let's find out, the density of any particular unit cell. So let's say the number of atoms within that unit cell is Z, right? Mass of those atoms, let's say the atomic mass is M, right? So Z into M will give you the total mass that is there in the unit cell, divided by what is the volume of the unit cell? That is A cube. This is density. Now this doesn't look familiar right now, right? Okay, let me make it familiar. We are not exactly aware of the atomic mass. We generally deal, atomic mass, has a unit of AMU. We generally deal with units, which are more real life, grams, kilograms, and so on. And that is why this small m, this atomic mass is basically equal to what? Molar mass divided by number of moles. That is exactly what has been substituted here. Zm upon A cube into Na. That is the density of the unit cell. So this is nothing but mass upon volume. Right, this complicated formula that you get over here, which looks complicated, by the way, it's not, right? This is still from mass upon volume. So density is not new. This is not new density that you're studying. It's still the same, right? Now, the questions that come on density, right, they're very straightforward. You have how many quantities here? 1, 2, 3, 4, 5. 5 quantities. Any one of them is going to be missing. You'll be given the other 4 quantities. You have to find out the 5th one. That is how it works, right? Okay. So that is exactly how it works. Now, let me try and solve this question. So density of a solid argon is basically 40 grams per mole. That is the molar mass, and its density is given 168 gram per mole at 40 Kelvin. The temperature. If the argon atom is assumed to be a sphere of radius that is given to you, what percentage of solid argon is apparently empty space? Right? Okay. So over here we are going to find out the empty space, the space within which is not occupied by argon. So first of all, let's figure out what is the unit cell here, right? And then within the unit cell, how much of the volume is occupied by the argon atoms? And then lastly, right, what is the volume of the entire argon atom which is there? So whatever is the leftover amount, that is the answer that we're looking for. In other words, this is 100 minus packing efficiency that you're looking for. So packing efficiency is how much of this volume is occupied. This question is asking how much of the space is not occupied, right? Okay. Now let's see. So over here, let me start. The density is given. Argons, this is given, and the size is also given. Can I find out the Z here? I can find out Z here. So my first point would be to find out Z. Z will give me the type of unit cell that I have, right? And from that unit cell, I can figure out the volume of the unit cell. I already know the radius of one argon atom. I know Z, so I know how many argon atoms are going to be there in the unit cell, right? Divide that and you have your answer, right? So that is, as simple as that, right? So a very simple question. I hope your, your doubt on density is clear, Ashutosh. Right. In the interest of time, I'm not exactly solving it here. Right. I will although post the solution to this in the chat. Right. Okay. Let's see. Please do a difficult arithmetic progression question. So Abu Zamani, I would definitely love to do that, but since this doubt session is on solid state, I'm not going to take that right now. But stay tuned, we will have doubt sessions on progressions and series as well. So that is when we will do a very difficult question on arithmetic progression. All right. Okay. So first three nearest neighbors of primitive cubic unit cell respectively are, right? The reason I took this question is because in this question a certain amount of imagination is required. So you're given the edge length. You're supposed to find out the distance of the first three nearest neighbors in a primitive cubic unit cell. This is one corner. The first nearest neighbor would be this, and this, right? So that is it. Now if the edge length of the unit cell is A, right, if the edge length of the unit cell is A, what is going to be the the distance of the nearest neighbors, right? The distance is still going to be A itself in this case. Now let me modify this question slightly, right? Instead of a primitive cubic unit cell, right, let me go for FCC. Right, so within FCC, let's say you're still given the edge length A, and you want to figure out the distance of the nearest neighbors, right, within an FCC. So remember in FCC, if this is the corner, the atoms in the corner are not exactly in contact. These are three other corners. The atoms which are in contact are basically these. Something like this, right? So we are supposed to find out the distance of the nearest neighbors, right? So over here, as simple as that, if A is given to me, I can figure out this entire diagonal. It is going to be root 2A, and therefore the distance between, let me change the color slightly. Yeah, so the distance between this is going to be just root 2 upon 2A, right? So a certain amount of imagination is only that is required over here. That is it, right? Now, so these are all the questions that I had, right? We will although have another doubt session on solid state itself, because I feel that even though you guys did not ask a lot of doubts on defects, I feel that that is something that we definitely need to cover. Defects have a higher probability of coming, even even if you consider boards or JE or any other examination, defects form a very important portion from which you could have passage based questions, you could have assertion reasons, you could have statements, which of the following statements is correct or incorrect, you could have all those kinds of questions. That is something that we need to cover, right? So I'm going to end this live session here, right? However, we will have another live session on solid state itself shortly. Although those who are not aware of this, right, like I said, I will share another article in which you need to post your doubts again. If you have doubts, in the topic that we have already covered, you can post that as well. I'll take it up again, no problem, right? Now, additionally, right, we have new tests which are being added, topic wise tests. So we have already started topic tests on redox and electrochemistry. We have finished solutions as well. As far as tests is concerned, we'll have a live session on solutions later, right? So apart from tests being added and live doubt clearing sessions that is being held, you can discuss all your doubts with students and experts. That's the most important part over here, right? Yeah, so that is what we have. Stay tuned everyone, all the very best, and good luck.